Picture the Mars we've all grown up imagining. A quiet, rust-colored world sitting patiently at the edge of what's possible, almost waiting for us to arrive, like an empty stage set up for humanity's next big moment. We've painted this picture in movies, dreamed it up in books, and talked about it as though landing there is just a matter of time, money, and enough political will. But that comforting version of Mars is a fantasy. It's a story we tell ourselves because the real picture, the actual physical truth of that planet, is far harder to accept. Mars isn't sitting there waiting for us. It isn't neutral ground. It isn't simply difficult in the way a tough mountain climb is difficult, something that rewards effort and persistence. Right now, Mars is functioning like a planet-sized rejection system, using the raw laws of physics with cold, mechanical precision to break down, push out, and destroy anything made of carbon that tries to settle on its surface. This isn't pessimism, and it isn't dressed-up negativity pretending to be science. It's simply what the numbers say once you stop romanticizing them and actually read them straight. The universe doesn't rearrange itself around human ambition. It doesn't loosen its rules because we're determined or clever or well-funded. And Mars, sitting roughly 1.5 times farther from the Sun than we are, has spent 4 billion years turning into something remarkably hostile, not out of any intention, because physics has no intentions, but through the steady, precise workings of heat and electromagnetism that add up to something that behaves exactly like active resistance. Here's the clearest comparison physics allows. Think about your own immune system, not the simplified textbook version, but the real, intricate machinery running inside every living creature, constantly scanning for anything foreign, tagging it, and sending out chemical attacks to break it down and push it out. Your immune system doesn't pause to consider your intentions. It doesn't care how brave or ambitious you are. It simply checks whether something belongs or not. And if it doesn't belong, every available defense gets triggered to remove it. Mars behaves the same way, just at the scale of an entire world. The moment something foreign lands there, a spacecraft, a habitat, a spacesuit, a human body, the planet's natural physics doesn't sit back and watch. Its chemical, electromagnetic, and radioactive systems immediately start working to break apart that foreign object's structure. And none of the forces involved are symbolic or exaggerated for effect. They are measurable, they are real, and they are deadly. Start with the ground itself, because most people assume solid ground is just neutral, just a surface things happen on. On Mars, the ground actively participates in the attack. For billions of years, the Martian surface has taken direct hits from ultraviolet radiation with no meaningful atmosphere to filter it. Earth has an ozone layer and a thick blanket of air that absorbs most high-energy UV light before it ever reaches us. Mars has neither. Its atmosphere is only about 1% as dense as Earth's, made mostly of carbon dioxide, and it provides almost no protection from ultraviolet exposure. In practical terms, this means the fine dust covering Mars has been cooked by high-energy radiation for geological ages, stripping electrons away from particles and leaving them permanently, powerfully charged with static electricity. And that charge changes everything about how this dust behaves, turning it from something you'd expect to just sit quietly on the ground into something closer to an active hazard, which is exactly where we're headed next. These electrically charged dust particles don't behave like ordinary dust sitting still on the ground. They actually lift into the air on their own. They repel each other, get drawn towards surfaces with opposite charge, and drift restlessly through the thin Martian atmosphere in ways you wouldn't expect from something as simple as dirt. This turns the Martian surface into something closer to a chemical battlefield than a peaceful desert. The moment a rover wheel rolls over it or a boot presses down, clouds of this charged dust get kicked up and cling stubbornly to whatever they touch. And this isn't like the dust we're used to on Earth, which tends to be relatively large, rounded, and chemically harmless. Martian dust is impossibly fine, with sharp, jagged edges shaped by billions of years of radiation breaking rock apart rather than water smoothing it down. It has never been rounded by rivers. It has never been softened by any living process. These particles are essentially microscopic razors, and because they carry an electric charge, they stick to fabric, camera lenses, mechanical seals, basically everything they come into contact with. The engineering consequences of this are serious. Every mechanical seal that a human mission would rely on, airlock seals, spacesuit joints, life support mechanisms, faces constant infiltration from particles that are physically built to scrape and chemically primed to stick. NASA's Mars rovers already experienced steady solar panel degradation from dust buildup that resisted even wind clearing it away. Human spacesuits, which need to bend and move thousands of times while keeping pressure sealed, would be up against a problem that current engineering simply hasn't solved. And if these particles ever reach human lungs, their sharp shape and chemical activity make them far more dangerous than any dust hazard found on Earth. The ground on Mars isn't passive. It's electrically charged, easily launched into the air by any disturbance, and shaped by geological chance into something that damages both machines and human bodies on contact. But the ground has a second way of pushing back, this time through chemistry rather than physics. Martian soil is heavily loaded with chemicals called perchlorates, powerful chlorine-based oxidizers that are aggressive toward organic material. On Earth, perchlorates only show up in small amounts in a few dry environments, and we treat them as toxic contaminants. On Mars, they're everywhere across the entire surface, at levels that would be considered a severe hazard anywhere on our planet. NASA's Phoenix lander measured perchlorate levels around 0.5% by mass in the soil it tested, and later missions confirmed this isn't some isolated pocket, it's a planet-wide feature of Martian soil chemistry. What makes perchlorates so damaging is almost elegant in a disturbing way. They pull moisture from their surroundings with intense chemical force, which inside a pressurized habitat or a human body could trigger serious cellular damage. But beyond drawing out moisture, they're also oxidizers, meaning they react with organic carbon in ways that release energy and tear apart complex molecules. The same property that makes them useful as rocket fuel additives makes them dangerous to living systems. And that danger reaches much further than most people realize, which is exactly what we need to unpack next. Perchlorates interfere with human thyroid function at levels far lower than what's naturally present in Martian soil. They would react with organic material in any food-growing system, contaminating experiments and breaking down the very molecular structures that farming depends on. Martian soil doesn't just fail to support organic chemistry, it actively works against it. The chemistry of that ground has been shaped by billions of years of radiation and geology into something built to break down carbon-based life rather than sustain it. Think about what this means for any serious plan to grow food on Mars. The dreamy image of glass-domed gardens producing fresh crops runs straight into a chemical reality where the soil itself is hostile to organic matter at a molecular level. Removing or neutralizing perchlorates is already a massive engineering challenge on Earth, even in small contaminated areas. Doing this at the scale needed to support Martian, farming would require processing such enormous volumes of soil that the energy and infrastructure costs become almost impossible to justify. In its own chemical language, the planet is telling us plainly that its surface isn't available for biological life to take root. And then there's the sky, or more precisely, what's missing from it that would normally protect us. The third way Mars pushes back doesn't come from the ground up, it comes from space itself, and it exists because of something Mars lost billions of years ago. Mars once had a global magnetic field. We know this because ancient magnetized rocks in the Martian crust still hold the imprint of that long-dead field, locked into their minerals from the moment they formed. But Mars's core eventually cooled and solidified, and the churning molten iron that generates a magnetic field through what's called a dynamo effect simply stopped moving. When that field died, Mars lost its single most important defense against the rest of the universe. A planetary magnetic field isn't just something that makes a compass point north. It's a massive electromagnetic shield that deflects the solar wind, a constant stream of charged particles blasting outward from the sun at hundreds of kilometers per second. Earth's magnetic field creates an enormous invisible bubble that redirects this stream around us, protecting our atmosphere from slowly being stripped away and shielding the ground from direct particle bombardment. Mars has none of that anymore. The solar wind hits the upper Martian atmosphere directly and reaches the surface below with almost no resistance at all, and the results of that unfiltered exposure are more severe than most people assume, which brings us to the next piece of this puzzle. This unfiltered exposure creates two major problems. First, the solar wind has been slowly stripping away the Martian atmosphere for 4 billion years, which is exactly why that atmosphere is now so thin it barely blocks any radiation at all. Second, and far more urgent for any human visitors, the Martian surface gets hit with a constant stream of high-energy radiation, including galactic cosmic rays, atomic particles flung to nearly light speed by distant explosive stellar events, along with solar energetic particles thrown off by flares and coronal mass ejections from the sun. The radiation level on the Martian surface runs about 40 to 50 times higher than what a person experiences at sea level on Earth. Astronauts on a mission to Mars would rack up radiation exposure fast enough to exceed the lifetime safety limit set by every major space agency, and they'd hit that limit in just a matter of months, not years. It's worth understanding exactly how this radiation causes damage. Galactic cosmic rays aren't light particles or electrons, they're bare atomic nuclei, stripped of their electrons, moving through space at a huge fraction of light speed, carrying enormous amounts of energy. When one of these particles passes through human tissue, it doesn't just deposit energy quietly, it carves a trail of ionization, damaging cells, membranes, and even the DNA double helix directly in its path. The breaks these particles cause in DNA strands are fundamentally different from the kind of damage life on Earth has evolved to repair. These are dense, clustered injuries that overwhelm the cell's normal repair systems and build up over time, raising cancer risk and damaging neural tissue in ways that no diet or medication can fully offset. Without a magnetic field filtering any of it, the universe is essentially firing an invisible storm of atomic particles directly at the Martian surface, and no wall of material thick enough to fully block it currently exists in our technology. There's something genuinely valuable hidden inside this harsh picture, though, because it forces us to look honestly at what we are and what Earth has quietly handed us without ever asking for thanks. We evolved inside a magnetic shield generated deep within a molten iron core on a planet that's still geologically alive. We breathe air that's been protected from cosmic erosion by that very same field. We walk across soil that billions of years of biological activity has slowly transformed into something that nourishes life instead of destroying it. We live beneath an atmosphere thick enough to filter out radiation that would otherwise tear straight through our biology. None of this happened by accident. All of it is the outcome of very specific planetary conditions playing out over very specific timescales, and together they produced exactly one place in this entire solar system where carbon-based life can exist on the surface without extraordinary technological help, which is a point worth sitting with as we head into what this all really means. The real value in studying Mars isn't the promise of a future home. It's more like holding up a mirror to Earth, showing us in sharp, honest contrast what our own planet actually is. Understanding how Martian dust becomes electrically charged and airborne helps us appreciate what it means to have soil that's been calmed and stabilized by water and living things over billions of years. Understanding perchlorate chemistry in Martian soil shows just how unlikely it is that Earth's soil, shaped by endless biological activity, became something that nourishes life instead of dissolving it. And understanding the unfiltered cosmic radiation constantly striking an unshielded planetary surface makes the invisible structure of our own magnetic field visible for what it truly is, not just scenery in the background, but a basic physical requirement for our existence in the first place. None of this planetary physics makes exploring Mars less interesting or less worth doing. If anything, it sharpens both our curiosity and our resolve. It asks us to approach Mars not as future settlers claiming some kind of destiny, but as scientists reading a message written into dust and radiation, a message that spells out with total precision the exact conditions life actually needs to survive, conditions that Earth, against overwhelming statistical odds in a cold and indifferent universe, somehow managed to meet. That's the real message Mars is sending us. Not silence, and not an invitation either, but something far more valuable. Proof, earned through measurement and hard mathematics and an honest refusal to look away, of just how extraordinary, how fragile, and how irreplaceable this pale blue world we already call home truly is. Take a moment right now to actually sit with that, because it changes how you look at the ground beneath your feet, the air you're breathing without a second thought, and the simple fact that none of it had to turn out this way. Earth isn't just one planet among many that happen to work out fine. It's the result of an almost absurdly specific set of conditions lining up together over billions of years. A magnetic field still humming along inside a molten core, an atmosphere thick enough to filter deadly radiation, soil transformed by life itself into something that supports more life. Mars shows us, in the starkest terms possible, what our world would look like without any one of those pieces in place. And that contrast is worth more than any romantic vision of red dust and glass domes ever could be. So the next time you look up at Mars in the night sky, or see another headline about a future human mission there, remember what its dust, its chemistry, and its radiation are actually telling us. This isn't a planet quietly waiting for us to arrive. It's a world that has spent 4 billion years becoming something that actively resists the kind of life we are, not out of malice, because physics doesn't carry malice, but simply because the conditions required for organic life to thrive are far rarer and far more specific than we tend to assume. Every layer of Mars, from its razor-sharp electrified dust to its perchlorate-soaked soil to its unfiltered blast of cosmic radiation, tells the same story from a different angle. Life needs protection that Mars lost billions of years ago and that Earth, remarkably, still has. This doesn't mean human exploration of Mars is pointless, and it doesn't mean we should stop studying it or sending missions there. It means we should approach it with clear eyes instead of comforting fiction, understanding exactly what we're up against before we plan how to face it. The truth revealed by Mars isn't a rejection of human ambition. It's a more honest starting point for it, one grounded in real measurement rather than wishful thinking. And that honesty is worth far more than the version of Mars we've built in our imagination, because it points us back towards something we too often take for granted, the extraordinary, fragile, and genuinely irreplaceable planet we're already standing on. If this kind of clear-eyed look at the science behind space exploration is something you want more of, subscribe now, because there's a lot more of this straightforward, evidence-based storytelling coming, and you won't want to miss where it goes next.